All right, today we're going to be talking about series circuits. All right, and well, we're going to be talking about two different types of circuits. And they're called series and parallel circuits. But the first type of circuit we're going to talk about series circuits, and we're going to talk about a really, really, really simple series circuit. And now, and now you see that. So on the left-hand image, you see this is how you'd see it on a Regents question, right? They would represent resistors, which is represented by R, resistance, resistor, uh, and a battery like this. And this is how they draw whatever object the electrons are flowing through. And so if you take a look at the right-hand side, you'll see a series circuit as well. And so this right here is a switch, right? On the bottom, this gold thing connecting these two wires. So if you press the button, if you push it down, you're connecting that switch. It works like a turn on button, right? So that's what you're. So if you think about it, any button that you're turning on or turning off has this type of switch that is connecting the wire. That's fundamentally what's going on. When you press the turn on button, you're connecting the switch so that electrons can flow, and that's why you have turn on the lights. You need to turn on stuff. Yeah. So the electrons go from the negative side to the positive side. And so you see the electrons going through these lamps, these tiny lamps. And so those lamps are resistors, all right? So these lamps right here, you can think of them as resistors. So that's R1, R2, R3. All right. And so in the past, in the past, uh, in some college courses, the convention of electron movement is from positive to negative, right? That doesn't make sense because it should go from the negative side to the positive side. But when Ben Franklin did what Ben Franklin did with electricity, he thought that it was the protons that were moving, right? Ben Franklin thought protons were the one that was moving and not the electrons. So that convention still exists to this day, like for some reason. I don't understand why, but for the most part, in real life, how it happens is that the electrons move from the negative side to the positive side. All right. So again, these lamps are these resistors, right? R1, R2, R3, R1, R2, R3, and this is the switch, and this is the battery. All right. So that's a series circuit. So what is the difference between a series and a parallel circuit, right? So you clearly see something right now. Well, parallel circuits have these lamps connected in parallel. Who knew? Who knew? And these series circuits have these lamps connected in series. Again, who knew? Who knew? So there are cons and benefits to both. Actually, there's more cons to this parallels. A lot of your circuits in real life are connected in parallel, right? Series circuits, not a lot of benefits, a lot of cons, and parallel circuits have a lot of benefits, not a lot of cons. But we'll talk about each of them later. So if you think about it, if you think about it, if you somehow this wire right here gets damaged, right? If you suddenly cut the wire here. So again, the convention is again from the positive to the negative side, which is clearly wrong, right? But I like this picture. Clearly, the convention of positive sign to negative sign is wrong because it's saying the electrons go from the positive side to the negative side, which is wrong again. So just ignore the arrow signs. Now, if you cut if you cut this wire right here, maybe on this side right here, what's going to happen is that the entire thing won't work anymore, right? All the electrons won't be able to flow because you just cut this wire. But let's take a look at this side right here. If somehow this light bulb gets damaged or this wire gets damaged on the top right here, electrons will still be able to flow. The electrons will still be able to flow on the bottom side. So even if one part of the wire gets damaged here, the other one still works. Whereas if one part of the wire gets damaged here, this entire thing will not work anymore. So that's a benefit to parallel circuits. That's why a lot of things are connected in parallel. If you think about it in the classroom, those lights on the top, there's a switch for each of those lights. Well, when in our classroom, I think there are two switches, and one switch turns on one stream of lights, and the other switch turns on the other two stream of lights. And if you ever noticed a broken light panel, only one of those panels are broken, right? So there are five panels on the top, and only one of them is broken. That's because it's connected in parallel. So even though one light bulb or one wire is broken, the rest of the light bulbs will work because you connected them in parallel. So that's parallel. But we'll talk more about parallel circuits tomorrow. So I actually just want to focus on series circuits today. So again, these are the difference in series and parallel circuits. If you think about Christmas lights, right? If you think about Christmas lights, well, if you look at the top, all these lights are connected in series. So if you somehow cut any one of these wires, or any one of these wires are broken, well, then the whole thing is not going to work anymore, right? The whole thing is not going to work anymore because it's broken. One thing's broken, everything else doesn't work. So again, we'll talk about parallel circuits later. So let's talk about conventions. I mean, not really convention, but about formulas. So on your reference table, on your page 4 of your reference table, you should see this formula, series circuits. And let's talk more about this. Let's talk about more. Let's about it's saying. Well, let's look at I. Let's look at I right here. The total current running through this entire circuit is equal to the current running through resistor 1, the current running through resistor 2, and the current running through resistor 3. So that's what this first formula is saying. It's saying that the total current running through this circuit is equal to the current running through each resistor. Well, how does that work, right? How does that work? How does it work? And that might be a little bit confusing for you guys, and it's very hard to conceptualize this. I had a hard time conceptualizing this when I was learning it, and I still don't have an entirely firm grasp, but I accept it. I have an analogy for it in my head, and I accept that analogy. Well, when I say I don't entirely grasp it, I grasp it. I 100% grasp it, but part of my mind wants to deny it, right? Part of my mind wants to say, no, that doesn't make sense. But I force myself to make that this makes sense. I force myself to. So let's take a look at this way. So let's take a tank of water, right? And so this pipe is a circuit. This tank of water is gonna, because the tank of water is at such a high level, it's gonna push all the water through this pipe into the bucket, right? So you can think of it. So this pipe is the current through which the water is flowing. Now, if you add some resistors, right? If you add some light bulbs, maybe you can think of them as obstacles. And so those resistors are obstacles here. And so you have these water running through, and now what's going to happen as you add these obstacles is that you're going to reduce the rate of flow. You're going to reduce the rate of flow. It doesn't matter whether or not these obstacles are the same size or not, whether or not they're the same resistance, or larger or smaller. The current running through the entire thing slows down now. The current running through the entire circuit slows down. Because sometimes it may not be correct to think of the resistors as obstacles that stop the water flow. The water flow passes through the resistors, but the water flow as a whole for the entire circuit is the same because you have this obstacle here. So when you take into account the entire circuit, when you take into account the entire circuit flow, the electric current is the same throughout everything because now you reduce the water flow throughout the entire thing. All right, so that's how you can think of it. So the current running through each resistor, each light bulb, is the same because you're taking into account the entire circuit, the entire water flow. It doesn't matter if you add the third obstacle, the water current will be reduced further, and it's going to be the same. All right, so the entire electric current for the circuit is the same. Now, again, we come to, so that's how you can make sense of that. Now let's talk about voltage and resistance. And so on your reference table, it says that for series circuits, your voltage is equal to V1 plus V2 plus V3. And it's better to think of voltage as a voltage drop. And so let's actually make something that says voltage drop. That's why, or rather, nah, I mean, voltage drop, potential difference, right? So I guess I should keep that in there. So voltage drop, potential difference. Think of it this way, your battery, again, if you take a look at this, you'll see positives, you see protons. Again, this is based on convention of Ben Franklin, and which shouldn't really be the convention, but because we're so used to dealing with, because it's been that way forever, people don't want to change it. But just, it's actually electrons that are moving, protons don't move, okay? I have to remind you guys again. So this battery is pumping electrons, right, through this thing, and there's a lot of potential, right? There's a lot of voltage. It's a high voltage. There's a high pressure, and as it goes through the resistor, right? As it goes through the resistor, what happens is that there's a voltage drop. Okay, there's a voltage drop, and so that's V1. That's voltage one, right? That's your potential difference. There's a difference in potential here. So the voltage drop here is V1. And then there's another voltage drop here, which is V2. And so the total voltage, the total amount of voltage that this battery is pumping from this place to this place, from this height to this height, is equal to the amount dropped by resistor 1. So there's a drop in voltage here and another drop in voltage here. And so the total drop in voltage is equal to the total voltage supplied by the battery. Alright, so the total drop in voltage is equal to the total voltage supplied by the battery, right? So there's a first drop here, there's a second drop here, and this battery is giving it voltage all the way back up to the highest point. Now, conceptually, it's very hard for students to understand this. Again, so students have an insanely hard time thinking about voltage, thinking about current, thinking about resistance. And it's fine if you don't understand this right away because it's going to take some time. And it's going to take some time. It's going to take some internalizing. You can't just instantly get it within 45 minutes. So I would bear with me here. So take your time to understand bit by bit. It's fine if you don't understand it right away. But it will take some time. It will take some time, right? And then your total resistance, let's say I want to talk about total resistance is easier to understand. So your total resistance through the circuit is equal to the resistance of 1 and resistance of 2. So that's just the fact, right? That's total resistance there. And you'll see that, yeah, so your total resistance is equal to R1 and R2. That's easier to understand. That comes easier to you. So now if we take a look at this electric current, you'll see the electric current is the same. Again, because your total current across the circuit, doesn't matter how much resistance you put, the total current across the circuit is the same. Because it's better to think of water flowing past them instead of as like a barrier. So again, the total current flowing through the resistor is the same. So I'll actually move on to practice problems. Oh, So again, the formulas are on the 4th page of your reference table. It's right over here. It's right over here. All right. All right, where is my tablet? So now let's see, number 1, the resistor, a 2 ohm resistor, so a 2 ohm resistor, and a 4 ohm resistor. So resistance of 1 is 2 ohms, resistance of 2 is 4 ohms. Are connected in series with a 12-volt battery. So your voltage is 12 volts, right? Your total voltage is total voltage. It's not voltage through 1, not voltage through 2, but your total voltage. If the current through 2 ohm resistor is 2 amperes, so if the first current is 2 amperes, okay, 2 amperes, the current for the 4 ohm resistor is what? So what is your current for the second resistor? Well, if you look at your series circuit formulas, right? If you look at your series circuit formulas, your total current is equal to I1. Your total current is equal to I1, is equal to I2, is equal to I3, equal to etc. So your current running through resistor 2 is the exact same as the current running through resistor 1. Again, I want you to explain this. This is how you explain it. Because the formula on your series circuit on your reference table, all the current is the same. That must mean that I2 must also be 2 amperes. And so that's B. That's B right there. 2. A diagram below represents a circuit consisting of 2 resistors connected to the source of potential difference. Alright, so what is the current running through the 20 ohm resistor? Now your resistance 1, right, is 10 ohms. And resistance 2 is 20 ohms. And your voltage, your total voltage is 120 volts. So there are 2 ways you can do this. And we'll give you the first way. So what is the current running through this 20 ohm resistor? Well, we don't know the voltage running through each. Well, actually, it's only one way. We want to know the total we only know the total voltage. We don't know voltage 1, right? We don't know voltage 2, so we can't do that. So we can't treat these resistors separately. What we have to do instead is that we know we have this formula. We know that my resistance right here is equal to V over I. So, but this is total resistance, right? This is total resistance, this is total voltage, and this is total current. I don't have total resistance, but what I can do is I can solve for total resistance. I can solve for my equivalences. That's what EQ means. So EQ means equivalent resistance, equivalent. So my equivalent resistance is R1 plus R2. And now I get 10 ohms and 20 ohms, and so I get 30 ohms. So that's my total resistance. So now what I can do is I can use this formula right here. So I can plug this in. My total voltage is 120, and my current, and I want to solve for my current, and then we get that on the other side. So that's actually, I'm going to erase the top part here, all right? So going over here, so we get 30 IT is equal to 120 divided by 30 divided by 30 is equal to 40 amperes. Okay, so that's your current. Oh, I'm sorry, can't even do math. 4 amperes. 4.0 amperes. I'm sorry. So that's your total current, and we know that in a series circuit, your total current is equal to the current running through each resistor. Okay, so that's the thing. So your total current is 4 amps, so it doesn't matter which resistor you're running current through, it's going to be 4 amps. And so that's the answer. Alright, so a circuit A has four 3 ohm resistors connected in series with a 24 volt battery, and circuit B has two 3 ohm resistors connected in series with a 24 volt battery. Now here is the tricky part. Here's the tricky part. Your voltage drop, and if you take a look at the GIF right here, if you remember the GIF, right, your voltage drop, so the voltage, you get to the same height, right? You can think of it getting the same height. So you have 24 volts up to the same height, and so up to the top. But here's where it's gonna be, here's what's gonna get tricky. Okay, here's where it's gonna get a little bit, just a little bit more tricky. Now, because, and so let's actually draw this. So let's say this is first drop, second drop, third drop. So this is, right, this is circuit 1, this is R2, R3, R4. And so this is your battery, right? This is negative, positive. And so there's drops here. So there's first drop, right? Second drop, third drop, fourth drop, and you get all the way to the end. So the total drop here is 24 volts. Okay, the total drop here is 24 volts. And let's take a look at circuit. And so this is circuit A, and this is B. I'm going to draw the same exact thing, right? So one, first drop, second drop. And so this is R1. Well, that doesn't, let's actually erase it. Okay, and so that's R1 and R2. Now, this is going to take some conceptual knowledge. So your total resistance, the resistance flowing across here is greater. So the total resistance is definitely is 12 ohms, right? So total resistance is 12 ohms. And because you have a total resistance of 12 ohms, the current flowing through each is lower. So, right, it's 2 amps. But your voltage drop here, you're still supplying the same amount of voltage. This is still 24 volts, which means that if it's still 24 volts, your total drop in voltage at the end is still 24 as well. Okay, so even though you have less resistors here, your total drop is still 24. Your total voltage drop is still 24. But because the total resistance is less, right? There's only a resistance of 6 ohms here. Then your current is only, then your current is just is greater because there's less resistance. But your voltage drop, the voltage drop still stays the same. It's still 24 volts. So the voltage drop is still the same here. So the answer is C. So again, this is one of the hardest for students to understand because it takes a lot of thinking to understand this. All right. It took me a while to understand why. I mean, I accepted it, right? I accepted it, but it took me a lot of just trying to think about why this works, how it works for me to understand it. So it's going to take some time. So your voltage, and number 4, your voltage is 9 volts connected to a 4 ohm resistor. So that's R1, and a 5 ohm resistor, and so that's R2. Let's actually write this vertically. 5 ohm resistor. So what is the current running through the 5 ohm resistor? So again, you're going to have to do, because you don't know the voltage running through each resistor, though you don't know the voltage drop, you have to calculate your total resistance first. And so that's R1 plus R2. So 4 plus 5 is equal to 9. 9 ohms. And now you're going to use this formula, R is equal to V over I, because this is total, right? This is total. You get 9 is equal to 9 over I2, or rather I total. And your I total is going to become 1 amps. But you also know that your current running through any resistor in a series circuit is 1 ampere. Okay, so the answer is 1 ampere. It doesn't matter which resistor it is, the total current running through a series circuit is the same. So the answer is A. So let's do number 5. A 10 ohm resistor. So that's R1, so 10 ohms. R2 is 20 ohms. When the current through the 10 ohm resistor is 2 amperes, so the current running through 10 ohm is 2 amperes. What is the current running through the 20 ohm resistor? So if you take a look at your formulas, you know that your total current in a series circuit is equal to each individual one. So if you know your current running through resistor 1 is 2 amps, then your current running through resistor 2 is also 2 amps. So the answer is B. A 30 ohm resistor. As a conceptual question. So it's asking you in this series circuit, compared to electric current running through a 30 ohm resistor, the electric current running through a 60 ohm resistor is what? Well, we talked about this in 2 questions. Your total current running through each resistor is exactly the same. Okay, so let's see. Alright, let's do 7. What's the total current in the circuit? So you have 4 resistors. R1 is 4 ohms. R2 is 6 ohms. R3 is 8 ohms. R4 is 6 ohms. And voltage is 12 volts. And so you're going to have, you want your total resistance first. So 4 plus 6 plus 8 plus 6. That's going to give you 24 ohms. And now you're going to use this formula, right? So 24 ohms is equal to 12 over I. So again, that's total. And now you're going to multiply this on this side so the i's cancel out. 24i is equal to 12. Divided by 24. Divided by 24. So your I is going to be 0.5 amperes because it's 12 divided by 24. So the answer is A. No, number 8. A 3 ohm resistor. 3 ohms. Arid. Is that arid? That's and. And and a 6 ohm resistor are connected in series to an operating electrical circuit. So if the current flowing through 3 ohm resistor is 4 amperes, so the current running through the first resistor is 4 amperes, what's the potential difference across the 6 ohm resistor? Well, if we know that the current running through the first resistor is 4 amperes, the current running through the second resistor is also 4 amperes. And so that's the total current. So what is the potential difference across the 6 ohm resistor? So there's a way to find that out. We're going to do R is equal to VI, V over I. But instead of being total, we're going to take the individual resistor. Because we want the individual voltage drop on the second resistor. So again, if you take a look at this, first drop, second drop, it's your battery. So this is R1, R2. They want V2, right? They want the voltage drop for R2. So this is V1 and this is V2. So they want V2. Well, how do we get V2? We use this formula. But instead of doing total, we're going to do R2, V2 is equal to the total current. Because the current is the same no matter what. So R2 is 6 ohms. V2 is what we will find out. I is 4 times 4 times 4, 24 volts. You get V2. So the answer is D. Answer is D. Are there any more questions? No, there aren't. Great.